Lesson 7L, Atwood machines with friction. Recall, a full Atwood machine is a two-body system where both masses are suspended over a pulley wheel. Direction of movement is due to the larger hanging mass. In grade 11, we will not calculate tension if the Atwood machine has any friction. Remember, we can redraw an Atwood in a single plane to help us calculate net force. However, you'll likely need to refer back to the original drawing for the direction of the acceleration of the masses. Let's look at this example of a full Atwood machine with a 15 kg and a 25 kg mass hanging across a pulley that has 5 newtons of friction force. Here's force gravity on mass 1. Force tension opposes force gravity on mass 1. Force gravity on mass 2. And tension opposes force gravity on mass 2. Remember, tension at both ends will be equal. Now if we straighten the Atwood out, we get this. Notice how tension looked like they were pulling in the same direction, but due to the pulley, they actually oppose one another. The same is true for the gravitational forces on mass 1 and mass 2. They seem to pull in the same direction, downwards, but they're actually pulling against one another. Which direction will the system move? Who wins a tug-of-war? Well, seeing as mass 2 is 25 kilograms, while mass 1 is only 15 kilograms, the system will pull to the right in a flat drawing. But in actuality, mass 2 will accelerate downwards, while mass 1 accelerates upwards in the Atwood. Since friction force opposes motion, we can now assign friction force to our drawing. If the system moves to the right, then friction force at the pulley is to the left. For our original drawing, that is towards the smaller mass, mass 1. So let's calculate the system's acceleration. F net equals force gravity 2 minus tension 2 plus tension 1 minus force gravity 1 minus friction force. Tension is the same at both ends of the rope, simply in opposite directions, so they cancel one another out. This leaves F net as Fg2 minus Fg1 minus friction force. Recall that force gravity is equal to mg, so subbing that in, we get F net equals to mg2 minus mg1 minus friction force. F net is 35 times 9.8 minus 15 times 9.8 minus 5. F net is 245 minus 145 minus 5. F net is 93 newtons. The formula for F net is ma, where m is the mass of the system, so we get m1 plus m2 times a equals 93. A equals 93 divided by mass 1 plus mass 2. A is 93 divided by 15 plus 25. A is 93 divided by 40. A is 2.325 meters per second squared. Let's look at the half Atwood with friction. This is a two-body system where one mass is suspended freely, while the other is resting on a flat surface like a table. Movement of the system is due to the hanging mass. If the friction force is large enough, then the system may not accelerate. It may not move. Again, with Atwoods, if there's friction, we will not bother calculating tension. Here's our half Atwood example. A 3.4 kilogram mass hanging from a pulley connected to a 15 kilogram mass resting on a table. There is a 0.12 coefficient of friction between mass 1 and the table. Here's force gravity acting on mass 2. Here's force tension at mass 2. Here's force tension at mass 1 and force friction on mass 1. Force gravity on mass 1 and force normal on mass 1. Since mass 1 does not rise above or sink through the table, force gravity 1 and normal force must be equal but opposite. That is, they have the same magnitude but different signs. Let's calculate force friction. Force friction is mu force normal. Force normal is equal to weight of mass 1, m1 times g. Force normal is positive though, since it points upwards, while Fg would be negative since it points downwards. Friction force is therefore 0.12 times 15 times 9.8, which makes 17.64 newtons. We will try to calculate net force without drawing the Atwood in a single plane this time. Who wins the tug-of-war, Fg2 or friction force on mass 1? Well, since 3.14 times 9.8 is roughly 35 newtons, and friction force has been calculated as 17.64 newtons, I would choose the force gravity on mass 2 to win. We can ignore gravity and normal forces on mass 1 since they cancel one another out. That makes net force equal to force of gravity at mass 2 minus tension at mass 2 plus tension at mass 1 minus force friction at mass 1. Since tension is equal but opposite at each end of the rope, F net is Fg2 minus force friction. F net is 3.4 times 9.8 minus 17.64. That's 33.2 minus 17.64. F net is 15.56 newtons. Since the acceleration of the system is in two planes, that is down for mass 2 and left for mass 1, it is necessary to keep those directions in mind when answering questions like acceleration, which we'll do next. To calculate acceleration, we'll use our F net value of 15.56 newtons. The formula for F net is ma. Since we are calculating the acceleration of the system, m is the mass of the system, m1 plus m2. m1 plus m2 times a equals 15.56. 15 plus 3.4 times a equals 15.56. A is 15.56 divided by 15 plus 3.4. A is 15.56 divided by 18.4. The acceleration of the system is 0.85 meters per second squared. For mass 2, that's downwards, and for mass 1, it's to the left.